Good afternoon. Thanks to everybody for coming. I understand security can be a very dry topic, so I'll try not to be too dry. One of the things that I will tell you is that I speak very fast. This is a 20-minute talk. Fortunately, it's right before the break, so if you have any questions, I love to talk security, and I love talking IoT. I talked the ears off of some people at lunch. So please feel free to ask questions when we have time for questions, and otherwise just absolutely just hit me up after this or at any time. I'll be here tomorrow as well. So first thing is, who am I? So I'm the Director of Engineering at LaunchKey. We're a security as a service company for multi-factor authentication. That's where I get all of this security knowledge. I'm a developer community activist in Las Vegas. Work with a lot of the user groups, hackathons, those types of things. I'm an IoT enthusiast. This picture of my first NodeBot that I made 3 years ago, International NodeBot Day, and I've been hooked ever since. And I'm also a national junior basketball coach, which is what I do in my spare time, which is why I'm leaving early on Wednesday to see the girls for practice. And we're here to talk about an uncomfortable truth. And that uncomfortable truth is that if you have an app or device, and the Internet of Things has that first word called the Internet. If you're on the Internet, you're going to be attacked. And there's just no way about that. If you have a device on the Internet right now, it is being scanned. It might not be scanned right this second, but sometime today, you will be scanned. If you watch server logs, if you've ever done backend development, you are constantly being scanned. Some of them are good, some of them are bad. And the other thing is that you will be exposed to a zero-day vulnerability. And if you don't know what a zero-day vulnerability is, that is a known attack that has not been made public, and you don't know about it until the attack happens. This happens all the time. And there's nothing that you can do about it except desperately try and fix your system to not have that vulnerability. And in the IoT world, there's been a lot of those going on, as you've seen right before the great security conferences in Las Vegas. They're talking about cars getting hacked and turned off on the road, people hacking into their systems, watching webcams, those types of things. Nest got hacked. There's a bunch of things that are going on that are just kind of scary. And because of that, security is just not optional. One of the big problems in the IoT world has been security, right? We've just been we're merging, we're growing, we're just hey, let's do this, let's do that, and let me sell this thing. And then all of a sudden, someone's got all of your user data, someone's watching your users, they know when you're home, when they're home, they're looking at their kids, and people are getting creeped out, right? So the important thing to understand is that security is like an ogre, it has layers. And that's the only funny thing I have today. And doing the layers isn't specific to security. It's any kind of risk management, risk aversion. They call the Swiss cheese analogy, which doesn't make sense because if you actually know cheese, all the holes connect. But the idea of this one is that you have holes at different spots, and with the idea that even if one layer they get through, there are the other layers there to stop them, which prevents a single point of vulnerability, which is the number one thing in security. Because you're not going to stop everything, you just have to stop enough. And the other thing is that you make it more difficult, so it increases the cost of penetration to an attacker. In security, it's all about increasing the cost, right? When you hash passwords, you do that to make it more expensive to break the password. It's not that they can't do it. It's not that they can't hack your system. You just have to make it cost more than the benefit they're going to gain. And that's the only way you can stay ahead of the game, right? The whole Moore's Law thing, it's not just about the IoT devices, it's about the things that people are using to hack your systems, right? These ASICs are getting faster and faster and faster, and they can break into systems, they can break your crypto, they can break your hashes. But you just have to make it very expensive for them to do that. And when we're talking about layers in the IoT world, especially in the node world, unless you're using embedded node, which some of you are and many of you aren't, you have to deal with all of these different layers, the operating system, the file system, the services, the application, your application, and then the network. And this is a 20-minute talk, and we definitely don't have time for that. So what I would suggest that you do is a good place to start is the Open Web Application Security Project, OWASP. If you've done web development, you've heard of them. They also have an IoT section, which is specifically talking about what do you do about Bluetooth, what do you do about these types of things, file access, because when you have a server application, it's in a server room somewhere that's probably secure. When you have an IoT app, it's in someone's living room. It's in a public place. So it's a little different. And the URL will be at the end of the slide presentation as well. So we're going to talk about things that are very specific to Node.js and how you can do that. I'm not going to get too lofty in concepts because you can read books about that and see blog posts about that. But how do you actually do that inside of Node.js? And one of the things that you want to be able to prevent is a man-in-the-middle attack. If you don't know what a man-in-the-middle attack is when someone gets between either two peers on a peer-to-peer network or a client and a server, and they're going to proxy the traffic, and they're going to steal all of your data. They're going to steal all of your traffic, all of your keys, all those types of things. And so when they become that proxy between the two systems, it's a big problem, but you can actually mitigate that in Node.js. And the ways that you do that is you require TLS. Most of you know it as SSL. I try not to use the word SSL because if you're using SSL, that's actually deprecated, right? SSL version 1, version 2, version 3, they're all deprecated. It's all now TLS, which is the transport layer security. And if you're using just core libraries, the only thing you have to do is you use the TLS library instead of the HTTP library, right? And you do TLS.request instead of HTTP request. If you're using the request library, it's already SSL by default if you use HTTPS in the URL. But one thing you have to make sure is that you don't ever set strict SSL to false, because that's not going to verify your certificate. If you're using a self-signed cert, find a way to make that work besides turning off strict SSL, because you will be vulnerable to a man-in-the-middle attack. Denying redirects. If you're using the core libraries, it doesn't matter. The way that they actually do this man-in-the-middle is they'll send you a redirect to go to their server, which has a valid cert. And you don't want to follow that if you're using the request library. And you can do that by one of the options. You can tell it as follow redirect as false. And then you can also do what's called pinning TLS certificates. We'll talk a little bit more about that because that's a little involved. And encrypting data. These are two of the things that we use at LaunchKey to ensure communications from any device, whether it's a mobile device, an IoT device, or server to server, that we're actually getting where we're supposed to be going. And for TLS certificate pinning, basically what you're going to do is you're going to be able to use the response that you get back from the server, right? So whether you're using request or anything else, you get this standard response object. It's the standard Node.js response object. And it, of course, has an associated socket. The response came on. And you tell it to get the peer certificate. So that is the other machine it was talking to. You want its SSL certificate, for lack of a better word. And that has a fingerprint. And that's the important part. So that fingerprint, you can actually, if you go in any browser and you go take a look at the information for the certificate, you're going to see the fingerprint of that SSL certificate. It's basically just a hash. Just like you do the same thing when you go verify the authenticity of a download file. You've got the hash that you can generate and verify. It's the same thing for an SSL certificate. And if you're going to do this, problems arise when you actually have your certificate gets compromised. You have to change it out. And if you're thinking, well, how does my SSL certificate get compromised? You think last year we had two major OpenSSL vulnerabilities that we had to, at LaunchKey, we had to immediately replace our certs because there's the possibility it could have been there. But in the year before that, you had Heartbleed. If you were in the server world, it was a very bad year because you were constantly patching OpenSSL and rewriting apps to use security better. So you want to have a backup so that you can quickly rotate it. And when you make these backups, you have to make sure that when you have these multiple certificates that you have a different fingerprint. And the only way that you can do that is you have to have a different private key in your private public key for your signatures for your certificate. And the next piece is encrypting data. If you want to make sure and have these layers, you have to make sure that when you're transmitting the data, you've got SSL encryption, but if your SSL is actually going to be compromised, then you also have to be encrypting data on top of that. And we make sure to do that as well. And you can do encrypt data at rest, which is data on your file system, data inside your caches, data wherever that might be. If you have a local database, you're going to consider encrypting the data in there as well. And if you're going to do that, you can use symmetric encryption. Symmetric encryption is basically both sides have the same information so that you can encrypt or decrypt using the secrets. And the problem with that is that you have to transport it. Both of you have to have that secret. So what I'm going to suggest to you today is you use what's called asymmetric encryption for anything you have to put in transit. And asymmetric encryption means that one of you has the capability to decrypt a message, and only one. The other one has the ability to encrypt it, but not to decrypt it. And that's what public-private key infrastructure does, is it allows you to take this public key that you can give to anyone, and they can encrypt data that only you can read because you have the private key. and you exchange those keys so that you can read each other's data. And it's going to be much more secure because the secret isn't passed along. If you're writing an IoT device, it has to connect to a server and it's going to be sending data back and forth. The moment you have to transfer that value, it's no longer secure because you haven't found a good way to encrypt it to send it. If you're doing peer-to-peer, you need to have them all they have to do is just exchange certificates through some sort of, like Bluetooth actually does the same thing, right? You do a pairing, you exchange your keys, you say, yes, I'm okay exchanging these with you, and now you can talk encrypted to each other and be really, really certain who sent the data, and that only the person that's supposed to be able to read the data can read the data. And then in the IoT world, especially if you're talking about small processors and small data, you might want to keep that message size very small. And the way that you can do that, and the way that we do that, is that we use a hybrid methodology in that you generate a key and an IV for your symmetric encryption, and then you take those credentials, the key and the IV, use that to encrypt your data, which is a small packet, and then you use asymmetric encryption to encrypt the key and the IV, and you send that along. So if you've got a fairly large data packet, and if you're using a large key set, it's going to make it a very large data packet, you can reduce that sum by using symmetric encryption on the data and then sending the credentials encrypted using asymmetric encryption. And both of those, symmetric and asymmetric encryption, are available native in the crypto package. And we'll go over a little bit kind of how to do that as well. Symmetric encryption. So the most important thing that you want to do for symmetric encryption is that you want to use a random initialization vector. And the only way to get an actual random value from Node.js is using the crypto package. If you've ever used any random generator, it actually generates the exact same sequence every single time. When they talk about random seeding, it just starts from a different place. So if you know the sequence and you know where it started from, you know what the next one is. So the crypto package has an actual random generator, and you can use get random bytes to get that random IV. And you always want to use some sort of blockchaining or cipher feedback to ensure pseudo-randomness. So if you take a look at the image up there, you can pretty much see that that's Tux, right? That's the Linux penguin, and this is actually not using cipher blockchaining. So basically what you do is you do the same cryptography on every single packet, every single block, and so it does the similar transformation. And so you can still tell, even though this is encrypted, it is not obfuscated. You can tell what data is in there, and then if you try to decrypt it, you'd only have to decrypt one block. Because if you get one block, you've got all the blocks. And what cipher blockchaining does is it takes the response and adds that to the next level of crypto. So it would look like complete fuzz if you looked at the picture. Plus, for the people that are attacking you and trying to get your data, they have to decrypt the entire package to know if they got it right, not just a single block. So nowadays, AES 256 CBC is available on most of your installs. I'm not sure about the embedded Node.js, but I know that if you're using some sort of Linux or Windows, it's going to be there. And 256 is a good strength, and your AES is a good cipher, and you want your blockchaining. So that'll be an option available most likely to you in your crypto packages when it asks you what cipher you want to use. You probably want to use AES 256 CBC. And the other type is asymmetric encryption, which if it's visible, and it looks like it is, the image you're seeing there is kind of the process of how just one side does one piece and the other side does the other piece. And that's how only you encrypt it one way and the other side can decrypt it. The RSA is the only included asymmetric encryption package, but it's good enough. It works very well, and we use that at LaunchKey as well. Your private key should be password protected. It's an option that you can password protect it, and basically what you're doing is you're encrypting it using a key, and you're going to decrypt it using that same key. So it's using symmetric encryption on your asymmetric encryption key. And it's a really good idea because of the way crypto works is you want to use a 32-character password or better. And since it's going to be in your application and you're not going to have to remember it, you may as well just do that anyway, right? It's a really good idea to have a large value for that. And because of the strength of crypto hackers out there, 2048 is the minimum key size. If you do SSH and you have a 1024 key, you should go change it today. 1024 is not enough. 2048 is the minimum. that you should ever be using. So the next piece that we talk about is account hijacking, and that's, of course, credentials. Never store plain text credentials. I know you think this is my IoT device, and it's just going to be stored here. Somebody gets in there, they get the credentials, they can get wherever they're going to get with those credentials, and it's just bad. You want to use strong hashing. So inside the crypto package is PBKDF2. It's not the strongest out there, but it's strong enough. It's not Scrypt, it's not Bcrypt, but it's good enough to do what you need it to do. And you're going to want to use, again, a 32+ character random salt, right? So if you have 2 accounts with the same password, they don't look the same, right? They're going to have randomness. 10,000 plus iterations. That may be a bit for something that's going to have a very small processor, but most processors today can handle 10,000 plus iterations. You just want to increase the amount of time it's going to take someone to decrypt your data. Anyone can break a hash. You just have to make it expensive. You have to make it take time. And you want to try and make it take like half a second. They're only going to have to log in once. They're going to have to verify that hash once. Use half a second. That's a really good idea. And make sure you're using a SHA-256 digest. So replay attacks, again, always use TLS, right? You don't want to make someone to be able to replay your data and affect your system. You want to use a nonce, and I'll explain that in a second. You're going to want to expire your requests so that they're only valid for a certain period of time. That's going to lead in with the nonce as well. And you want to sign your requests so that you can verify that this data is actually what this individual sent. And for nonces, it's just a random value that's used only once. It has to be cryptographically random, so you're going to want to use cryptum, get random bytes again. And it should expire, because you're going to have to remember what this is so that someone can't send it again. And you don't want to have to remember it forever. So you should make sure that your nonces are going to expire. The same thing goes with your request. So if you send a request, you send a timestamp with it, and you say, I'm OK with a minute, then you only have to remember the nonce for a minute, because that request is no longer valid after a minute. And digital signatures are just a variable hash of supplied data, right? So you're just going to hash the request, and you're going to send it along. And if you're using, you can use either HMAC, which is symmetric, or you can use RSA, which is asymmetric, and you want to use asymmetric if it's at all possible. It's preferred because it's being transmitted, right? And a lot of this stuff gets kind of confusing, especially if you have to build it yourself. And we did the same mistake at LaunchKey, where we built our own scheme for putting in the signatures and figuring out all the data. And the problem was that what we didn't realize is there's a standard, right? There's a very good standard for JavaScript. It's called Jose, and it is the JavaScript object signing and encryption standard. And it's going to have a really nice way for you to be able to put in, here's my header information, which tells you how I did this, and my data, and then here's my signature. And that's super important. And when you're signing your data, when it says a verifiable hash of the supplied data, it's important that you include things that are important to that request. We had a bug that was never actually utilized, but someone found it, and we paid them to find it because we care about security. In that you could take the same request, which was a read request, change the message to be, instead of a GET request, you change it to a delete request, and it deleted the data. Even though you weren't authorized to do that, it just took the call and said, oh, this is a delete request, and it's signed and it's valid. So you could do a replay attack and do something you weren't supposed to do because the entire message wasn't signed. So you want to sign the location. You want to sign what the method is. You want to sign the headers that are valuable. It's important to, when you're doing crypto, to also understand HTTP, to know what actually includes a message in a REST request. And I know I just went through a ton of stuff really fast, but I do have like a minute for questions, and then does anybody have any questions? Yes?
What options do you have for a pipe that's really thin, where you can really count only bytes at a time?
A few bytes at a time. You're going to have a really tough time doing anything there unless you're going to basically, the first byte is this the position, and the second byte is this is the data. You're going to have to almost invent your own protocol at that point. But if you can send data in bytes like that, then you can send encrypted data in bytes like that. So if you have like a byte that says I'm the beginning and a byte that says I'm the end, you can certainly pass the encrypted data that way. It's going to be larger, though. There's no way to get around that. Is there another question over here? No? Okay, well, hopefully this has kind of spurred some ideas. I know that before I started working for LaunchKey, I thought I knew about security, and it blew my mind what I didn't know and what I should be doing. So if any of this kind of spurred any questions, I'll be here to answer questions for the rest of the day and most of tomorrow. So please, please, please let me know if you have any questions. All right? Thank you very much.